Это включите презентацию, пока я представлю вас всех. Good afternoon to everyone.
Good afternoon.
And welcome to the Winter Online School on Computer Engineering, Applied Artificial Intelligence and Robotics. We are very glad and we are really happy to see all of you today. And let us start with a brief presentation of Tomsk State University so that you can realize and understand all the opportunities the university can provide to you. And I am going to introduce you a representative of the International Affairs Department of Tomsk State University, Anna Tikhonova, who is going to give you a brief presentation of TSU. So Anna, you are very welcome. Анна, у вас микрофон выключен. Мы вас не слышим.
Так, секунду. Так, сейчас слышно? Hello, everyone. My name is Anna. Tomsk State University is a university with great traditions. It's literally a region of knowledge, and over the course of its long history, spanning a century and a half, the university has trained more than 150,000 professionals who work now in different industries in Russia and abroad. Tomsk is not a very big city, but there is a high percentage of students in it, so there are a lot of places who can provide you some entertainment, some youth-oriented establishments that you can go and just enjoy. Basically, it can be called student city, and if we tell about its ranking, so it's 85th best student city in the world and third in Russia. Also, there are some famous names in its history, even some Nobel laureates in Tomsk State University. For example, Dmitry Ivanovich Mendeleev, who wrote a university charter, even was considered a rector of our university. But then other person was selected, Ivan Petrovich Pavlov, Nikolai Nikolaevich Semenov, Jean Henry Dunant, the founder of Red Cross. So many people who are famous not only in history of Tomsk State University, but throughout the world. Also, we have some famous alumni. You could see them on the screen. It's Kim Yon-nam, Galushko, Grechana, Kuybyshev, Plevich. Among them, there are 3 prime ministers, 2 ambassadors, 2 current governors, and others. So a lot of famous and prominent people. About the rankings. As you can see, our university is second in internationalization among Russian universities and 107th in the number of international students. You could say that it's quite high number because we really have a lot of international students who could communicate not only with Russian students, but among themselves. And here is rankings by subject. We are 191st in natural science and among the top 200 in physics and astronomy. In computer science, it's 400th among the world universities. If we are talking about Tom State University everyday life and infrastructure, it's 21 faculties and institutes, 145 departments, more than 3,000 international students from 70 different countries, and number of students is continuously increasing. We have 12 programs taught in English. Of course, if you want to study programs that are taught in Russian, it's also available, and we have pre-course department, and you can take preparatory courses and study in our university or any other Russian university. Among the most popular programs are software engineering, applied mathematics and computer science, economics. If we are talking about master's programs, it's also applied mathematics and computer science, fundamental computer science, information technologies, mechatronics and robotics, and others. And of course, we have also some popular PhD programs, biological science, chemistry, mathematics and mechanics, and others. In Tom State University, there are many opportunities for research and development of science. People are doing research work and making different discoveries. We have 3 research institutes, more than 40 leading research schools, and more than 60 world-class laboratories in which Russian and foreign sciences work. Among our key partners, Seoul National University, University of Tehran, University of London, and others. And of course, we have many industry partners. Actually, it's more than 750. And when you're our student, you can take an internship in the companies with which we have partnership. It's Google, Huawei, Siemens, Samsung, Microsoft, and many others. Tom State University is the first Russian university to have signed memorandum with the UN Habitat. If you don't know, it's memorandum for human settlements in sustainable urban development, which goal is to promote socially and environmentally sustainable towns and cities. So you could say that it's quite noble goal, and we are participant of it. Also, Tomsk State University is the only Russian university that has joined the collaboration at the Large Hadron Collider at the European Organization for Nuclear Research. And of course, some information about campus life, about our dormitories, facilities, and other things. Our campus building are in the center of Tomsk, so it's quite easy to commute. And if you're living in the dormitory, that's max 15 minutes, maybe, walk from dormitory to campus. As I have said before, we have dorms. It's they're new for international students, and they have all the facilities that students could need. And of course, I can't forget to mention about the living expenses for students. Dorms is around $14–15 per month. Hostel around 8–10 maybe per month. And if you want to rent an apartment in the city, it's approximately 200. And monthly expenses for food is usually no more than 150. But of course, it depends on you mainly. Also, we have some sport clubs that you could join and develop yourself in these fields. So our sport clubs annually hold and organize over 1,000 events at both the university and city levels. For example, university health days, freshman's holiday, athletics run, Mile of Peace, and others. Traditionally, on Sundays and holidays, free student sport days are held throughout the academic year with the number of participants over 60% of full-time students. So it's quite a bit high number. Also, we have students that are winners and prize winners of all Russian competitions and are part of Russian national teams in athletics, weightlifting, powerlifting, and other fields. Here you can see Anna Kovalenko, who is Associate Professor of the Faculty of Physics Education and who was, for the first time in her career, the champion and record holder of the World Games. And in July 2017, Anna set the record and won 3 gold medals at the 26th European Diving Championships in Wrocław. So it's quite an accomplishment. And if we were talking about sport, now I think it's time to tell more about culture. Tom State University is at the heart of it, or the heart of arts. We have different clubs which students could join or just visit concerts to enjoy and have a good time. For example, students' music theater or CMT show. You don't need to have special education in this field to join. Just enjoy it and want to be a part of it. Rock club, which was created for students who are fond of music, play in groups, and want to create their own team of develop solo creativity. Actually, it's the name Rock Club, but it accepts musicians playing in absolutely any genre, from pop to black metal. Dance theater mirror, where performance is not just a dance, but a theatrical performance with its own psychology and its own characters. And of course, I can't not mention jazz orchestra Su-62. It's one of the favorites of the Tomsk public. It has quite a big repertoire, and there are different genres that they perform. So if you will be in Tomsk one day, I recommend you to visit their concert and just enjoy their music. Thank you for your attention and thank you for your time.
Thank you, Anna. So once again, my warmest greeting to all participants and welcome to Tomsk State University and to the online winter school on computer engineering. And let me introduce one more person. This is Professor Dmitry Shashev, who is a Deputy Dean at Tomsk State University, and he is a Deputy Head of the Master's Degree Program on Computer Engineering. And he is going to introduce a research aspect, research part of our Master's Degree Program. So Professor Dmitry, the floor is yours.
Thank you very much. Greetings for everyone. I'm glad to see a lot of people here. It's great. And let me share my screen. Okay. Everything good? Okay. Once again, I'm glad to see you here, and I really appreciate your interest in robotics. And let me say a few words about our faculty, in particular about our master's program, which has the same name actually as our winter school, Computer Engineering, Applied AI, and Robotics. For your understanding, if you will choose us, what you will gain actually. If you see, we focus on some special skills and knowledges in the following areas. The first one, automated information systems. data mining, integrated information system, mathematical and system modeling, UAV, actually unmanned aerial systems, robotics and embedded systems, computer-assisted vision, system simulation, and digital twins. But one more thing I wanted to say, that actually we focus on different types of mobile robotics. It can be unmanned aerial systems, it can be unmanned ground systems, and so on. And on the right side, you can see our dean, and actually the director of this program, Professor Stanislav Shidlovsky. He's also here. And here's also, you can see Tatiana Rumyantseva. I guess you've already known her, but she is our program manager. And if you have any questions in future about our program, about how to join us, you can ask her. And also, as you see on the left side of the window, the QR code, you can use it to learn more about our program, about our faculty, and our research projects. Let's move on. Sorry. Here is actually the curriculum of our program. It consists of the 4th semester. You can see the main subjects you've got. And actually, I wanted to say about the following. As you see, in the end of each semester, special subject named research work. It means that our students start to research from the 1st semester during the whole program. And our supervisors, our professors help you individually with everything. Let's move on. And here you can see some of our research topics, no, actually possible research areas for you. No, actually we consider different researchers in field of robotics, and the main thing, as for me, you have a chance to run your personal research related to AI and robotics with the help of scientific advisors and join current projects in our laboratories. Our faculty includes 4 research laboratories. The first one, Robotics Laboratory, Laser Laboratory, Medical Tech Laboratory, and Computer Vision Laboratory. And actually, if you are our student, you will get access to the following equipment. Some of the vendors which produced the equipment we used, actually, you can see on the slide. And let me tell a few words about our projects. The one of them is ScoutBot. This is a remote control scout complex for radiological, biological, and chemical surveillance. And this is a video how it works in real life. This type of robot was made by the staff of our laboratory. And can be controlled remotely and autonomously also. I guess you understand, if you are interested in such type of robotics, you're welcome to join us. Another big field of our research is UAV and different subtopics of UAV field. Actually, we focus on autonomous control systems, and also we work on SLAM navigation. Maybe some of you familiar with such type of algorithms. One of the modern approach in the navigation of any robot, simultaneous localization and mapping. This is also one of our projects named Drone Hunter. It was a project about development autonomous control system for UAV, high intellectually control system. The idea was to track, recognize another drones on board without using any ground stations or cloud systems or servers and so on. One of our projects with our industrial partner, one of the biggest one in the field of UAV in Russia, the name of company is Gyroscopes, and we work in the field of small cargo delivery with this company. Okay, let's move on. And here you can see also the examples of students' projects. Which have already done actually, but one of them, algorithms for detecting UAV by audio signatures, intelligent control systems, analyzing wireless security standards, intellectual automated information system, and so on. Okay, that's it from me. Once again, thank you for your participation. And if you will have any questions, if you are interested to join us, first of all, use the context of our project manager, and another thing, use QR code to see more about us actually. Thank you very much.
Thank you, Professor Dmitry. And the last greeting is from me. The last greeting for you is from me. I am going to give you a very brief overview of our winter school and what we are going to do during the week. So, as you know, as I have already written to all of you, all the participants may get a certificate of completion from Tomsk State University, which you can use as you want, but please pay attention that to get this certificate, you need to attend at least 2 workshops and complete at least 2 practical tasks and fill in the final winter school test. As for our master's program, this certificate will allow you to get extra scores to your entrance test exams and a discount up to 40% for the tuition fee for our master's program. So this is a great chance for you to use this opportunity and not only to get some extra knowledge and in skills in robotics, but also to become a part of our master's program. And as for the program, of course, you all know and you will able to get acquainted with it on our website. And once again, today we are going to have a first workshop, which is approach to intelligent drones. And please pay attention that tomorrow and on Friday, you will be doing your practical tasks so that you gain some practical skills. And of course, you will have a chance to contact speakers, to contact your advisors and ask different questions. Let me show. This is a website that you have that you all know about. This is our site of our master's program, and you have these buttons on the front page, so you will not be lost. When you press upload your reports, this is a button to upload your practical tasks, and there will be a special space to ask questions. So if you have any questions and there are some issues for discussion with your advisors and speakers, feel free to ask anything you like. Here are again our contacts, and so my real pleasure is to introduce our first speaker to you. This is Maynak Mandal, who is our graduate, who is a graduate of master's degree program. And Maynak, my warmest greetings to you and welcome, welcome. And you are the first speaker. You are respected, and so we are very glad to see you today. The floor is yours. So meet our speaker Maynak Mandal and his master class, his workshop, Approach to Intelligent Drones. Maynak, you are welcome.
Thank you, Tatiana. It's been a pleasure working with everyone. It's really nice to see Professor Shilowski and Professor Dimitri, and really nice to see a few of my friends here. And I'm really glad to see so many people attending this workshop, this winter school. And today I'll be speaking about Introduction to Programming Drones. And let's get started. Okay, so I'll just share my screen and then introduce myself a bit more. Just a second. Yep, so here I am. And today on our project, on our winter school, Introduction to Programmable Drones. Let me tell you that I was a former student at the National Research Downstate University and in the faculty and the program you're seeing, Applied AI and Robotics. And if you can see my screen, let me know. I hope you can see my screen and hear me well. Yes. Okay, that's great. So yeah, let me tell you a bit about myself. I am a doctoral researcher at the University of Connecticut at the moment, and I'm working closely with Professor Shilowski and Dimitri as well for my PhD from TSU, and I'll get a PhD from here as well. And yep, here is my contacts. If you want to contact me at any moment, please go ahead and do so. It's written on the side. It's there. I have an email, I have a phone number, and of course a GitHub page. And for my task, I'll show you that I have made a GitHub page for my task. If you can see here, you don't need to worry about the schematic details right now. I want you to go home, well, you're already home. I want you to go back. I want you to install these softwares, probably in a virtual machine, or if you want, I can give you an ISO and you can download that and then install the repositories that I'm going to be showing today. And at the end, I have given a task, make a video or record multiple screen or take multiple screenshots and upload it to the given portal. That is the given task here, and all the instructions of how you need to do it is given here, as well as the references of what you need to do. I'll give you the link to this at the end after my presentation, so you can take your time, install it on your own at your own pace, and finally use this for a reference while you're submitting your tasks. Here you have a bit more referencing for troubleshooting, and you can use it as and whenever you want. This is always there. Okay. So going back to my presentation, yep. As as Tatiana told you, that I have done we have multiple projects at TSU, the Faculty of Innovation Technologies. I also have done various projects, including the drone hunter that you just saw. It was one of my greatest projects at FIT, and I really loved working for it. But everyone has to start somewhere, and this is Programming Drones. And I'll give you a basic introduction of how drones are made. I'll have an itinerary over here. Just an introduction of how drones are made. Then the parts, if time permits, or if you guys want, I can show you a video of like our faculty assembling a drone. Then if time permits, we can show you calibration and tuning if needed. And then I'll talk about onboard computers, as well as the ground station called Ground Control, and programming if time permits. We have 2 hours, so I'm not going to go into very detail about programming, but of course, feel free to reach out. I am a drone enthusiast, and of course, I can help everyone who is interested in learning about drones. Okay, so the major parts of a drone are basically the flight controller, the frame, the motors, the propellers, the RC controller, and the ground station, if that is optional. The flight controller is basically the heart of the drone, as it controls all the movements, takes an RC controller inputs, and translates the inputs into outputs for the motors. And then the frame holds everything together. The motors, of course, you need it for flight. The propellers are needed to connect to the motors to generate thrust, and then the RC controller to actually control the drone. And the ground station, if you want to do autonomous tasks, if it is supported by the flight controller, you can do autonomous tasks using the ground station. Okay, yeah. We want to focus today on autonomous drones. Okay, the requirements for good autonomous drones are that we need a drone or a flight controller which has good support with integrated technologies, like the Pixhawk or the DJI NASA or something like that. Okay, these controllers can be integrated with other ground control system softwares so that we can use it for autonomous tasks, waypoints. We can even control them using our own code. The controller that I'm going to be using today is called the Pixhawk for this demonstration. And I have a drone here if you want to see. I don't have the Pixhawk right here with me, but I can show you. We have people who can show you the Pixhawk if you want to see that. We need a good onboard computer if we want to do advanced tasks like image recognition and SLAM and everything. We need a good onboard computer on that. And of course, we need good tuned PID rates. So anyone, I don't know how advanced you are, how frequent you are with drones, but if you need a good flight, you all know that you need good PID rates for the drones. If you want, there's a huge topic there. You can write a thesis on how to tune good PIDs. So I'm not going to be going into them. There are various guides online. But again, if you want any help on them, you can of course reach out to me. Yep. So tune PIDs are a must. Okay. Let me get into the introduction a bit more. Okay, a flight controller is a small circuit. Let me tell you what flight controller is first. Yeah, a flight controller, or FC, is a small circuit board of varying complexity. Well, of course, yeah. Its function is to direct the RPM of each motor in response. Just a second, we have another guy. Okay, in response to the input. A command from the pilot for the multirotor is given to move. It is fed into the flight controller, which determines how to manipulate the motors accordingly. And once you manipulate the motors, you can generate thrust. You can go ahead and move the motors accordingly. Okay. Then, of course, the major components that I told you earlier inside the flight controller are the onboard sensors. There's usually a gyroscope, accelerometer, barometer, and etc. A lot of sensors in it, so that it can accurately recognize the state of the drone and then make adjustments to stabilize the drone or move the drone according to the user input. There has to be a sensor interface connection, or basically something like UART, I2C, PWM, serial, SPI, etc. Like you need to connect your flight controller to the motors. You need to be able to connect your flight controller to different external sensors if required, something like a GPS maybe, or maybe an external EMO. Okay. Then there is an actuator control interface for PWM. Like basically, if you want to connect your motors, you can connect your motors using this interface, that is the pulse width modulation interface given in the PICSOC. The interface connects to the ESCs of the motors, and then after that, it connects to the motors. You can also connect a servo depending on what you're flying, because some people might actually go into planes instead of drones. You might need to change the ailerons and avions so that the drone, so that the plane flies properly. Of course, you need a CPU after that, because you need to process the input and generate an appropriate output, and some memory. Okay. And the major functions of the flight controller are basically, it sits between the radio controller and the motors, and it allows you to control how the UAV flies, how smoothly, how aggressively, how you want to fly it. It provides a total interfaceability. So you can, like, it's the hub for everything. Your onboard computer can connect to this to control it. Your RC controller can connect to this. Your video transmitter can connect to this. Like, it's a hub for everything. It also has a mixing algorithm. Just a second. Yep. Yep. It also has a mixing algorithm for the motor. So for example, you give pitch, roll, thrust, and these commands are given by the RC controller, and it needs to be converted into output for each motor, or the PWM signal for each motor, PWM signal for each motor. Yeah. So this is done by a mixing algorithm. If you want to read more about it, you can read it on the GitHub page, or you can read about it online, but I'm not going to go into it because it's already established and developed by the time I'm speaking right now. Yeah, and of course it provides basic stability functions for flight. Okay, before I go in, let me just show you, just a second. I'll just, yeah, let me tell you about the orientation of UAVs, if I can draw on it. Hope you can see. Yep, I can see now. Just a second. Okay, so I'll tell you the directions. Let's say this is the UAV. Sorry for my bad drawing. Okay. So we have multiple axes, how the drone can be controlled, right? One is moving the drone up and down. Okay. This is the altitude, the direction movement, and if you change the height, it's done by giving more thrust to the motors, all four of them. That is thrust. This is one of the axes. Okay. Then if you want to move the drone in this way, forward, that is this way, that is called pitch. Pitch, where the front motors slow down and the back motors speed up. So what happens is the drone tilts forward and then moves forward. Okay, that is pitch. Then there is roll, if you want to do the same thing in another direction. That is moving this way. Okay, where in the, well, either the right-hand side motors or the left-hand side motors, both of them speed up and the other one slows down, where it tilts in the direction it wants to move and goes to the direction, that is roll. And then there's the final axis called yaw. Just a second. Yeah. That is basically moving the UAV in a lateral axis on the same point. So basically, if the drone is turning clockwise and counterclockwise, basically if the drone is turning clockwise or counterclockwise, that is yaw. If you want to know more about this, of course, contact me, but this is a basic introduction movement of the drone. Okay, and this, of course, is controlled by the flight controller. And so basically what the flight controller does, once more, is it takes in commands of thrust, roll, pitch, and yaw, and moves it, gives it to output for 4 motors. So for example, we have a quadcopter. So it will give you outputs for M1, M2, M3, and M4. Okay. So it gives you output from thrust, roll, pitch, yaw to M1, M2, M4. It needs to distribute the thrust and the roll and the pitch and the amount of yaw for each motor into this. Okay. Moving on. Let me just clear out the screen. I hope you could see the drawing I was making. Yep. Let me just remove this. Yep. Just a second. Yep. Yeah, sure. Okay. So there are several flight controller support for this thing. So most flight controllers are divided into F1, F3, F4, F7, and H7 flight controllers. These are basically the processor chips inside the flight controller. So inside the microcontroller unit. Okay, the processor is the brain of the flight controller. It is similar to the CPU in a computer. There are currently 10 series of STM32 microcontroller units. From faster to slower processing speed, there are H7, F7, F4, F3, F2, F1. Like you can see, you can get the point, right? Yeah. Okay. So the slowest one is F1 and the fastest one is H7. As you can see here, the processing speed varies from level to level. That just a second, yeah. The most common flight controller that you can get for cheap is the F4 flight controller, and it's the most commonly used because it is used for hobbying, it's used for advanced robotics, like you can use it for a lot of stuff. F4 is the way to go if you are into, well, if you want to build a cheap drone, okay? But of course, for our project, we're going to be using an F7 flight controller because we're going to go into advanced autonomous drones. Yep, okay. Moving on. Once we have a flight controller, we need to choose the firmware what you want to use. So for firmware, that's basically the software that controls the functions of the flight controller. So of course, there are open source firmwares as well as closed source firmwares. Since we are an open university, we're going to be going for open source firmwares. Of course, we work with closed source firmwares as well, but getting into closed source firmwares, as you know, would be harder than open source firmwares. So there are a lot of open source firmware like Paparazzi, OpenPilot, then Tau Labs, MultiV, and so much more. Okay. Going on. So once we get to open source firmware, we have to get into the drone racing, of course. There are so many open source firmwares that go into racing, like RaceFlight. That is one of the most used flight control softwares for using this thing. Now it's not very popular because it's old and not a lot of people use it, but when it was released, RaceFlight was one of the most used flight control softwares out there. Okay. Everyone currently uses Betaflight. I myself use Betaflight as well as this thing, Autopilot, but Betaflight or RaceFlight or whatever I'm showing right now basically does not include autonomous movement. It has basic autonomous movement, but it's not used for professional autonomous work. The most professional autonomous work, this thing. Just a second, I can see that my drawing is still visible. Let me try to clear that out. Just a second. I'll try to. Just a second, I can see that my Screen is still, this thing is still visible. I'll stop sharing my screen and reshare my screen. Yep, we're back on. So, yep, okay, moving on. Yeah, as I said, one of the most used firmwares for autonomous movement is Autopilot or PX4. PX4 is an open source flight control software for drones and other unmanned vehicles. And this project actually provides a flexible set of tools for all the developers to share technologies to create tailored solutions for drone applications. PX4 provides a standard to deliver drone hardware and support the software stack, allowing the ecosystem to maintain and build a hardware and software in a scalable way. Maintain hardware in a scalable way. Anyway, the PX4 is, well, it's one of the most advanced softwares out there. But one of the problems that we at FIT noticed whenever we were working on it was that its PIDs needed to be tuned a bit more finely than Autopilot. Autopilot had a more robust PID system where we could just not tune the PIDs at all and fly them, and it would still fly fairly fine. And well, Autopilot, of course, is the leading open source autopilot system for multi-copter, traditional helicopters, fixed-wing aircrafts, rovers, submarines, and antenna trackers. We are going to be using this firmware. Well, yeah, we're going to be using this firmware for our tasks. Okay. And of course, you don't need to have it because we are going to use the simulation environment, the SITL, it's called SITL, software in a loop, where this firmware is going to run on your computer and then give you an interface to work with, which I'll show you eventually. I'm not going to show you the install part. That's your homework. You're going to install everything according to the guide at GitHub on my GitHub page. Yeah. And after that, you're going to do the task and submit it. It's not very hard, but it will take about an hour or two if you time. So maybe an hour approximately. Okay. So since I told you about open source, I'm going to go into a bit about closed source. There are multiple flight controllers that are closed source, the flight control software that are closed source basically. There is DJI light bridge based, anything like DJI N3 or DJI A3. Then there is KISS. And there is the closed source firmware that was used in DJI Rise or Tello. It's the one of the cheapest drone in the DJI's lineup, and it flies really well. Okay. Okay. So going on, there is an onboard computer, as I said, which connects to the flight controller to give you extra flight functions. Again, let me draw just a second. Let me draw something and show you. Give me 1 minute. Yep. So let me draw again. Let me just here. So I'll give you what an onboard computer does in a more detailed way. Let's say this is the flight controller, a new color right now. And then there are the motors. 1, then 2, then 3, then 4, and so on. You can have as many motors. You can have a hexacopter, quadcopter, and so many different motors. This is the flight controller, which is connected to the 4 motors. There are multiple sensors. S1, S2, S3, and so on. Okay, and these sensors, of course, include, as I said, barometer, EMO, gyroscope, accelerometer, and so on. Just a second. Yep. So this is connected to an RC receiver, which can be connected or paired with a transmitter, TX, okay, which will transmit via radio waves and connect to the RC receiver to give commands. And this will convert the commands from this thing to PWM signals. or pulse width modulation signals. These are values for the ESC to understand to change the voltage of the motors accordingly so that the motors generate different speed. Different motors work differently. Of course, I'm talking about DC motors, but of course, most drones use brushless AC motors. And again, you still control it the same way using pulse width modulation. Okay. Now, where would you attach an onboard computer? The onboard computer usually, of course, goes on the drone itself, and it connects. It connects to the flight controller. Okay, so the onboard computer usually runs Linux or some form of Linux. Well, it can run anything, of course. It can have whatever you want, but the idea is that it will run a control software which will give control commands to the flight controller instead of the TX over here or the transmitter. So basically what you're making is making the drone autonomous. Of course, the flight controller can source basic autonomous control commands like go to this GPS point, move right, move left, have this value as an output. Of course, it can do that without the onboard computer. You can do it as a ground station using an extension of RC called the telemetry. I'm sorry, you can't see that. Just a second. Telemetry, it's a radio, just like the RC controller. Yeah, but it connects, of course, again via RC to a ground station. This is also a computer which controls the flight controller using the telemetry over here. Okay, but to replace that, a lot of people, well, most people usually use an onboard computer and a control software to control the flight controller or the drone itself. The benefits of this, let me clear the screen. Yeah. The benefits of this is that your onboard computer, just a second, can have interfaces to multiple things. For example, a lidar, a sonar system, a sonar array basically, sonar array. It can be connected to cameras, like maybe monocular, or basically depth cameras, or array of cameras. Just a second. Array of cameras. The same array that you see in smartphones these days, you can have your own chip, and of course you can connect it to the OBC and write your own control software to take in the information from the camera array and use it accordingly. Most people use 2 cameras or basically a depth camera and be done with it, because that is all we need these days. Okay, so let me tell you a bit more about onboard computers. Okay, onboard computers basically are required for major computations, and this can be controlled remotely. Of course, if you have an onboard computer, you can run software on it, but the best way is usually to remote into it and then ask it to do some tasks. Of course, the scripts and the programs need to be loaded onto the onboard computer before. There are various examples of the onboard computer that is basically multiple. You can use a Raspberry Pi, you can use Orange Pi, you can use the NVIDIA Jetson DX1, NVIDIA Jetson DX2, NVIDIA Jetson Xavier, then Jetson Nano, Intel NUC, basically any computer, any small computer that you can fit on the drone and the drone can fly with it, you can use it as an onboard computer. Well, yeah, you need to be you need to be able to interface with it from the flight controller, of course, because there are some small computers you don't have any interfaces with. I'm talking about you, MacBook. But anyway, yeah, so you can use any of these. Let me tell you that the Jetson was used, well, it was used in one of Tesla prototypes to give the advanced LAM algorithms that it uses for autonomous navigation. The Jetson was once used in them, but now it's not. Now it has its own in-house this thing. But yeah, the Jetson is a really formidable onboard computer, and we use it on most of our projects. Okay. Well, let me just clear the screen again. Yeah. So as I told you, remember, tuned PIDs are an important part of a drone because you need to have, let me just show you, like, instead of me saying it, let me just show it to you how smooth a drone can be after it has a tuned PID. This is a fairly windless day, and this, like, fairly windy day, sorry. And this drone barely moves, if you can see. It's in the air, I'm standing right below it, and it's just stable in the air with no problems whatsoever. That is the benefit of having a tuned PID. Let me just move it forward. I go below it as well. And you can see the drone is as stable as it gets. Okay. And this is another example where I'm moving the drone. And at the moment I left the sticks, and you can still see the drone moving really well. Yep. So if you're going to build your own drone, I suggest reading up about PIDs or reading about PIDs, and of course tuning your drone. I'm not going to go into the PID, what is the PID system, everything. Anyway, so let me tell you where a smart control, basically the smart control can be applied in drones. So this is basically the control structure of a drone. Well, let me just annotate if it can be better. Yep. So, okay. So this is the, excuse me, the controller of the drone. The output basically is the output of the 4 motors, basically the movement. It's just really bad, just a second. Yep. As you can see here, the output is referring to basically the output of the drone. So we have 4 motors in a drone, or you can have multiple, but in a quadcopter you have 4 motors, and the changes the motors apply in the real environment. So for example, if the drone is moving forward in an XYZ plane from 0, 0, 0, that is called the output, like XYZ for easier understanding. Yep. Then this output is read by the position reference system over here. Okay. This position reference system will, of course, estimate the yaw. Well, you usually use a compass, but anyway. And then it goes through a position controller. Basically, it will convert the world, the like XYZ, from the world frame to the body frame, so that it understands what orientation it is in, and then adjust the pitch, roll, and yaw accordingly so that it moves. As you can see here, this is the outer loop of this part is the outer loop of the controller, and the inner loop of the controller basically runs with 4, basically roll, pitch, yaw, and thrust. As I told you earlier, these outputs are given to the mixed motor mixing algorithm, which will translate, of course, as I said, thrust, roll, pitch, yaw to motor 1, motor 2, motor 3, and motor N. So you can have n number of motors, and your motor mixing algorithm will convert your thrust, roll, pitch, yaw to this. And you can read about it, of course, online. It's called the motor motor mixer matrix, and I'm not going to do that again because it goes into a lot of detail of how it works, and it's, well, even if you had the time, it's quite difficult to understand at the first go. You'd rather want to stick to software at the moment than going to hardware. Of course, if you love hardware, you can of course reach out to me and we can get into the details. Let me clear it out again. Yep. So just a second. Yep. Yeah, the output is of course read using the sensors and estimation algorithms over here. And you can read the system states. Basically, we have another person who's entering. Yeah. So we can read the system states from the real environment using multiple sensors, as I said, inside the flight controller. And then again, it will go to the position reference system over here, and we'll use that for smart control. The smart control of any drone occurs after the outer loop controller loop. So the controller, of course, has its own reference frame for converting the world frame to the body frame, or basically converting XYZ into a quaternion so that it understands the orientation of the drone. But smart control usually, most of the time, happens after the outer loop of the controller, where we adjust the pitch, roll, and yaw PIDs, or we give such commands to the PID controllers for the internal loop controllers so that the drone moves in a way which we want, basically. So as I said earlier, you can have lidars, you can have cameras. Let's say you want to track something using a camera. You write a program, maybe in Python or whatever. You track, let's say, an X object, and then you want the drone to follow it. So let's say the object is moving in the Y direction, basically forward. Okay, the drone will adjust its pitch accordingly so that it will move forward using the camera's command. So you need to convert the frame of the camera to the body frame of the position, to the body frame of the robot, or basically the UAV. And for that, you're using onboard computer, which will tell the PIDs, like the inner loops of the mini drone or the drone, basically, to move to an X, Y, Z point so that it adjusts accordingly with reference to the object that you're tracking. Okay, moving on. Let me tell you that, well, as I told you, let me remove the, just a second. Yep. It should be clear now. Yeah, so let me tell you why we are using Autopilot. Basically, Autopilot, as I told you, it's one of the most advanced flight controllers. And I'll tell you why we're using Autopilot for our projects. Basically, because Autopilot is one of the most stable flight systems out there, and it's basically, it can be used in most flight controllers. If you can see here, I have examples. There's the Autopilot that came out in 2009. It's a really good flight controller, and no one should use it right now because it's very unstable. Then there's APM 1.2, which was also pretty old, but well, you shouldn't use it at the moment because it's old. The most used flight controller out there is Pixhawk 1, that is over here. Just a second, if I can. Yeah, Pixhawk, that was released in 2013. Yeah, the Pixhawk that was used in 2013, but it's also pretty old now. In the video that I'm going to be showing you, we're going to be using the Pixhawk 4 controller built by our very own engineer. Well, with my help, Misha. Anyway, so we have multiple other boards which you can use, and these are this flight control support in the right. You can see that how many boards the Autopilot supports. That's the Beagle board, there's QAV, there's multiple, everything that can be used with this. But anyway, let me show you the video of us building the drone. You can see it here, just a second. Let me just share. Yep. Let me know if you have problems viewing the video. Hope everyone can hear. Hey guys, this is Pas Manak, and as I already have told you, we're gonna build the drone today. We're using the S500 platform from Holy Bro, and you'll see how to assemble it. Let me tell you that I have some annotations with this thing, or basically I'm voicing over here. If you have any questions, let me know over the chat or send me an email. We can get into that. Okay, this is the build part of the drone. Then before we begin, I want to show you all the parts we're going to be using today for assembling it. This here are the arms of the drone where you'll be attaching the motors, and this will attach to a base frame which will finally look like a quadcopter. The circular edge is where you'll be attaching your motors using 4 screws, and the triangular edge is where the arms will attach to the base frame. This here is the base frame where there are 2 layers. One is the power distribution board with the plus and minus, where you can see there. And here are the motors. These are brushless AC motors. There are 3 terminals where you need to connect your ESC. This finally here is the ESC. Again, as you see, there are 3 banana connectors where you'll connect your motor. There's a plus and minus to power the ESC, and a signal on the ground to send signals for the motors. This is the bottom part of the base plate where you'll be attaching your battery using the strap provided. These are the legs. As you can see, these are carbon fiber legs, and this will be attached to the base frame. And these are 2 carbon fiber rods which will be used to hold all of the frame together. And these are the 4 propellers that we're going to be using, 2 counterclockwise and 2 clockwise. This here is the Pixhawk 4 platform. It's the flight controller and the heart of this build. The flight controller, as you can see here, contains a lot of connectors where you can connect various peripherals to the flight controller. This is the ESC. Once again, this is the motor, and these are the banana connectors. This motor is a 2216 880 kV motor. Yeah, I forgot about this. This is the RC receiver. This is how we'll be controlling the drone. This is the telemetry module. One is for the ground and one is for the drone itself. You can connect it to the computer using this module. This is the power distribution board of the flight controller, where you will connect all the motors and will connect the battery. This will power up the flight controller itself as well. Yeah, this has the FMU outs and the IO out as well. Yeah, so yeah, let's start assembling the legs and connect it to the base frame. In between, I might speed up the video. Please don't mind. Yeah, so it is suggested to connect all the parts of the drone using screws, but the screws should be using a component called Loctite, so that you're using, while there are vibrations, they don't shimmer off. As you can see, I'm using the blue liquid. That's this thing, Loctite. Quickly, while moving on, let's go ahead. Here, I would suggest that you use an electronic screwdriver for faster operations, but either way, it's up to your preference. As you can see here, we connected everything. Now we are going to be connecting the way how we'll connect the carbon fiber rods into the base frame using the same methods. As you can see here that I'm pointing the screwdriver towards the front, that means the drone will be pointing towards the front accordingly. You can change according to your preference. Yeah, as we can see here, I'm gonna be connecting the power distribution board, and I'm gonna be using 2 screws, but we have a problem, as you'll notice soon, that the screws don't exactly align, as you see. So it's okay to leave it like this, but it's better if you connect, if you make it more secure using zip ties. You can find a more compatible power distribution board which is suited towards your frame. We didn't have one at hand, that's why we're using zip ties. So you need to make it really snug and, you know, put it in properly and cut off the extra bits. Now we have quite a lot of the power frame assembled. You can see it's starting to take shape. And check that it's put in snugly. And remember that you have a plus and minus for the battery with an XT60 connector, as you can see here. Here you'll be connecting all the motors. Each motor has 3 major connections, that's ground, signal and VCC. There are 4 here, but 3 should do the work, and I will be connecting 3. This is where you'll supply power to the flight controller. This is where you will put the IO PWM in from the flight controller. An IO PWM in connects the flight controller to the aux ports in this board. I'll tell you about aux ports later, but yeah. Those are the signal pins, the small ones. Yeah. Let me get some things. Just now you'll see I'll be soldering the ground positive and the signal. There are 2 grounds technically, but if you connect it to the same ground, it doesn't matter. For better connections, I'm using 3 different pins. But we do it for all the 4 ESCs, as you can see here. By the way, at any point, if you have some problem, please leave your comment and I'll address them after the video. Yeah, so we have 4 ESCs soldered, and now we can put in the final top frame and check that. Before we do that, we need to check that all the connections are snugly made. And we need to put in the IO for the IO port so that we can connect it later to the flight controller. This will connect to the main outputs. The main outputs will power the motors. Connect the plug here for the power. Your power distribution board might have a different connector, but the one we have provided to us by Holybro has this kind of a connector. The ideal way to assemble the frame is to pass the motor wires underneath the frame so that in the event of a crash they are protected. And again, you have to use Loctite. You should. I mean, it's a very good idea because the drone vibrates a lot when it's in the air, and if you use Loctite, they won't shimmer off and come off basically. So see, I'm assembling it. Moving on, now we can assemble the motors, and as you can see here, we need to align the screw holes over here and place it. Again, using Loctite so that it doesn't shimmer off. And this is where it's more important, or the most important, because the screws from the motors have fallen off in various of my builds because I was lazy and didn't put Loctite on. We do it for all of the 4 motors. Yeah, make sure to correctly put in the direction of the motors. They are clockwise and counterclockwise. This build uses the T-motor motors, and they have self-tightening props, and so be careful when you are putting that in. I can explain this part later, but it's one of the beginner mistakes everyone makes. Moving on, putting the base frame, top part of the frame. As you can see, there is an arrow which points towards the front of the drone. Again, using Loctite, we securely tighten the screws. Yeah, I hope you can see them. And I'll tighten them a bit more securely. A good suggestion would be, if you want to make the drone, if you make some mistakes, it's easier for the first build that you don't use Loctite. Go ahead, fly it out, see if you have any problems, and then reassemble the drone using Loctite, the blue liquid. You can see here, it quite looks like a drone now. Now let's look at the flight controller. I've already attached the flight controller using 3M tape, or vibration dampeners, to a vibration dampening plate. This part is not compulsory, we just had one in hand, it was going to waste, and that's why we used it. You can see that there are 2 plates separated by 4 rubber spacers, which will dampen the vibration, as you'll see. You put it in properly, and now while it's assembled, you can see that while it's flying, it can dampen the vibration, since it will be suspended over. Now we'll be connecting this, not placing this to the part of the frame, so we'll clean it properly because we will be attaching it using double-sided tape. You see how it lines correctly, and it should face the front according to the frame. Well, this part is not as important if you are into custom builds, but either way, we're going to be using 3M tape provided by Holybro. You can buy them separately if you want, but these are really good tape just to attach. This tape is really good to attach on this thing. So we clean it up a bit more. The ideal place for the flight controller is near the center of gravity of the drone. But if you can't place it there, you can place it anywhere you like, but in the correct orientation. it should manage correctly if it has a good processor. After you stick it, pick up the drone using the flight controller to check how well it's placed. Now, since everything is attached, we can connect the power cable from the power distribution board to the power connector of the flight controller. And we need to connect the IO PWM plug to the IO PWM of the flight controller so that it can send signals for the motors. Now, if you require, you can use a GPS module, and of course it has a compass in it, so you have to make sure that it's pointed in the same orientation as your flight controller. This has about a 7 centimeter long plug, not a plug, it's more like a stick to make sure that it doesn't have any, interference from the motors. And as you saw here, now this is the RC module. Pretty simple. This is the telemetry module. Once again, it's for 33 megahertz. Has a micro USB connector and a normal connector, a normal pin for the big socket. So once again, we'll be removing 2 screws here and aligning it correctly. As you can see, the arrow should be aligned, and we'll be connecting putting the 2 screws back so that it'll be snug. Our build had a problem because it used to shake a bit, but we put some double-sided tape to fix that. And then we connect the GPS pin to the GPS input of this thing, a big socket. And this is the telemetry plug and the telemetry module. We connect it to the telemetry one of the PICSOC. You can have different connectors according to your board. And of course, we need to make a connection from the RC module to the RC in of the flight controller. Once everything is connected, make sure everything works, and you place it on the frame the best way you can. The ideal place for the RC module is somewhere near the flight controller, making sure that you can have the 2 antennas in a 45-degree angle or a 90-degree angle. As you can see here, we're going for a 90-degree angle. We're gonna put it in 2 different arms and secure it using zip ties or the electrical tape. And we clean the area so that we can attach the telemetry module using double-sided tape. Again, 3M tape is used. You can use any other double-sided tape, but 3M tape is preferred because it's really strong. As you can see, I'm going to be connecting it using electrical tape. Ideally, you'd like to save as much weight as you can, even grams count, but this is fairly a big drone and it doesn't matter that much over here. I mean, a few extra grams wouldn't hurt, but you'd prefer not to. Now you'll connect the 3 banana connectors to the banana connectors of the AC. Here you shouldn't have any problems because you have banana connectors, and even if you make a mistake, it doesn't matter. You can connect any pins to any pins. Later, when we're turning it on, we'll check the direction of the motors and correct it as required. To change the direction of the motors, you don't need to change anything. Take any 2 pins of the banana connector and just switch them in the ESCs. It'll automatically change the direction of the spin. direction of the motors actually. Now that it's fairly assembled, like almost the part is done, we'll test it using a 1500 mAh 4S battery. Let's go. Yeah. I'll connect it to the X360 connector of the power controller board, and as you can see, all the lights start up. And as we know that everything is working. Now we need to get the carbon fiber rods and place it so that it can hold the battery holder. As you can see, we'll be doing it right now. This is the battery holder, as I said earlier. You place it like that and put it in. Now that it's assembled, let's start testing the direction of the motors. We put in the battery. The ideal quadcopter frame should have 2 clockwise and 2 anti-clockwise. It's not ideal, it's always the case that 2 clockwise and 2 anti-clockwise. They should be opposite to each other. Now that I've armed it, you can see that I can spin the motors and see the direction of the spin. You can touch the motor slightly and check which direction it's spinning. This motor is spinning clockwise. Yeah. This motor is spinning anti-clockwise, and this is clockwise. So there is one motor wrong, and I'll show you how to fix it. Just take out 2 connectors of take 2 banana connectors out and interchange them. So you can see here I'm doing that. Once again, we'll put the motors into testing motor arm and then see which direction it's spinning. Now it's spinning correctly. Now we connect the self-tightening propellers. Well, usually all the motor propeller pairs will have some form of indication, like here we have silver heads and black heads. The black heads will go to the black top part of the motor, and the silver heads will go in the silver part. We'll connect them and make them snug pretty much. It's necessary to keep in mind that the direction of the spin of the screw of the motor, where you'll be attaching on the propeller, is on the it's screwed opposite towards the actual spin of the motor, so they self-tighten when it flies. Now, as you can see here, we are gonna fly the drone. I have a friend with me, and now you can see it'll take off and it flies beautifully. Well, these drones or these controllers have a really good processor, and they can usually fly really well even without tuning. But in a later video, in the video after this, I will show you how to tune the quadcopter. Now, as you can see, it flies fairly well. You should check if everything is working. If you're happy with the tune, you can just fly with it. But usually a fine-tuned quadcopter flies much better, and makes you feel happier. And there you have it. Now you have a quadcopter that flies. If you guys want any consultation, you can ask after this about building the drone. I can help you with that. And that's a graceful and successful landing. Hey, so, okay guys, if you have any questions up until now, let me know. I can address them right now before moving on. If you are interested in the programming part, if you're interested in more controlling the drone accordingly, we can go according to that. If you have any questions, send me a chat or unmute your mics and let me know if you have any questions about whatever I've taught up until now. I can see everyone's names. Okay, so someone has asked for my email address. Let me just give it to everyone. That is my personal email. You can reach out to me anytime. And for my university email address, you can go for manak@mail. Just a second. True, as well as manak.edu. These are my university email addresses. If you can, of course, if you need anything, just let me know. These are this thing. Yeah, Surjit, you asked me which version of the Raspberry Pi should be used and what would be the RAM. Depends on what your application is. So if you want to do advanced, maybe some image recognition or image processing, you should at least have 2 GB of RAM. That is what I would suggest. But of course, 4 GB and 8 GB are welcome. I think we should have a video showing where we have a 4 GB RAM version. I think we should have a video. Just a second. Let me show you. I think this is it, right? Yeah, this is me. Yeah, so this is me flying with the 4 GB RAM version. It doesn't have any image recognition as such, but I'm controlling it with the keyboard and mouse instead of a RC controller. I think you'd be pleased if what you can do with 4 GB of RAM, and depends on your programming skills as well. Hey, so I have a question. Which version? Of course, yeah. You told me that you have some issue with object recognition with Raspberry Pi with 8 GB RAM, which is too slow. I used OpenCV. Can you suggest? It depends on what kind of program you're running. Can you please let me know? Like, you can directly talk to me. You can unmute your mic and we can have a conversation right now, Sarojit. I get it. If you're not comfortable, it's not a problem. Oh, it's not a problem. It's okay. Since you have an audio issue, can you let me know what were you trying to do with OpenCV? Yeah, sure. We can discuss later. No problem. You can send me an email. You have my phone number. You can always reach out to me. We can discuss it because I do have a program, as far as I remember, in GitHub where you can see. I also have used OpenCV. Just a second. We're not going to be going into this, but I'm just giving you an example. If you can use, I'm just tracking something using this thing, OpenCV, and I used a simple mask to, do this. Anyway, I have a video that I can show you later if you want. If you have any problems, just let me know. And I don't know why you had problems using a Raspberry Pi. Usually for these kind of applications, the Raspberry Pi is usually enough. But of course, depending on what you're doing, if you're going to be tracking, you're going to be tracking something in real time, it might be difficult to achieve with the Raspberry Pi, but shouldn't be a huge problem with the latest Raspberry Pi 4. Yeah. Raspberry Pi 3, like the older versions of Raspberry Pi, were a bit slow for our applications, but now Raspberry Pi has stepped up this game, and it's amazing to see what we can do with small computers. Yeah. Okay. So moving on. Up until now, does anyone else have any questions? If not, I can. Yeah. Okay. Samuel. Yeah, is MATLAB the best for programming drones? Is it okay? Of course, it's okay to use Python. Using Python is one of the best things. For a MATLAB model, of course, you can use a MATLAB model. It's not a problem, but using Python gives you more control. So MATLAB just makes it easier. That's it. Python gives you more control. You can fine-tune everything using however you want to. Definitely go ahead with Python, depending on what you want to do. Yeah. If you have any other questions, nope, I can move on to the calibrating tuning. Don't worry about it. I'm going to be sharing the videos. Yeah, of course. Don't worry about it. I'm going to be sharing the videos later with you guys, probably at the end of this video, or I could just post a link to my GitHub over here. I'll add it. I haven't uploaded the videos yet, but I'll add it over here as a reference so you can view the videos as well. Yeah, the videos might be a bit choppy for you because you're watching it over a Zoom link, but if you want, definitely I'll upload it on, well, somewhere, maybe on Dropbox or somewhere. Don't worry about it. Okay, so if you have no questions, let me just see. Yeah, if you have no questions, we can go ahead with the calibrate and tuning part of this thing. Yeah, the GitHub link, sure. It should be, just a second. Go ahead. Here. There is the instructions with the task of what you need to do. Sorry, no. To everyone. Here, if you can see. I sent the GitHub link, and you can read the instructions of how to set up your software environment. So you can use CTL. If you can see here, all the instructions are there with the references and the tasks that you need to do. Again, no issues. Yeah. So I'll be uploading the videos and sending them to you, adding them on the GitHub page over here. You can watch them at your own pace later. Okay, so let me go ahead into the calibrating and tuning part of the video. If someone wants me to go into the connections in more detail, or how the system is structured, let me know. I can draw out what we just showed in the build part of the video and then explain different things depending on what you guys need. Okay, let me just show you this thing, the calibrate and tuning part. Yeah. Just a second, let me just make it easier for optimize for video clip. Yep. Hope you can see now everything. I'm going to be muting my mic. Hey guys, once again, this is Past Mana, just a bit ahead from the last video. In this video, we're going to learn how to tune the drone, and in the last video, we learned how to build the drone. Let's start. Before that, we have to install an SD card in the flight controller, as you can see here. Usually an SD card is provided with the flight controller, or you can use any cheap SD card like 4 gigs or 2 gigs, not a problem, it's just to store logs. The application we are going to be using today is called Mission Planner, and to do that we have to connect Pixhawk flight controller to the computer using a micro USB cable. There are two major firmwares out there, that is PX4 and Autopilot for using in the Pixhawk flight controller, and today we are using Autopilot. As you can see, the controller boots up after you connect the wire. Here you can see that this is Mission Planner, specialized to work with Autopilot. First, to install the firmware, you need to click Install Firmware Legacy or Install Firmware, and then select whichever drone you have, a quadcopter, hexacopter, octocopter, plane, whatever. We are going to be using the Ardocopter over here because you have a quadcopter. Ardocopter quad, I mean. It will select and it'll download the firmware from the internet. It'll erase the board and automatically flash the firmware into the flight controller. Once it's done, you can probably restart the controller and connect over here. To restart the controller, you need to open the wire and connect it again. Once it's connected, as you can see that it's downloading all the parameters, and it shows up as a green bar which is downloading the parameters from the flight controller. Now it's untuned. Not untuned, it's untuned. It's also uncalibrated. You need to calibrate the compass, you need to calibrate the EMU and the level. This is the orientation screen where you can see all the information. To check properly if it's aligned in the frame, there are two red lines which says this is aligned to the ground, and if you move the flight controller, the whole ground frame moves. This here shows that there is no GPS because we are inside the room, and this controller supports 2 GPSs, so that's why GPS 1 and GPS 2. We are using the GPS 2 module, that's why we've disabled the first GPS module. Here you can see all the modes that you can configure. There is auto, loiter, and whatever. And here are the gauges where you can see the speed and everything else. These are a live display of all the parameters that are being broadcasted, and these are the messages sent by the flight controller or being broadcasted by the flight controller. Here you can download the logs of every time you fly, you'll have a log and you can download it. Here you have the information about the BBM signals that's being sent. This is the map, downloaded from Google Maps, where you're going to be flying. We are in Tomsk, and that's why we are going to be in one of the nearby stadiums. You can set your home position, you can add waypoints, you can add a lot of stuff from the planning menu. Now that I've shown you how to install the firmware on the Pixhawk flight controller, I'll teach you how to calibrate everything and then tune it, or you can fly without tuning, but anyway. But you should remember that you should always calibrate it before flying. Here is a battery that we are going to be using. It's a 4S 5000 mAh battery, 5200 I think. So as I said earlier, you have to use the provided strap and attach it accordingly, as you can see in the video. This is my friend doing it. Now it's important to remember that whenever you're calibrating or tuning the drone on the ground while it's connected to the computer, you should always remove your propellers before doing any kind of tests, because if anything goes wrong, you will not like it. Now we'll connect the XC60 connector. As the controller boots up, we'll now connect to the drone using the telemetry module. We'll connect the antenna to the ground version of the telemetry module and use the USB cable and connect to the same software mission planner. With the telemetry module, you can't flash the flight control, but you can do everything else. Once you've connected, it'll download parameters just like usual. And now you can see that as you move the drone, the orientation changes in the software. It's a bit laggy because of the delay between the telemetry module and the ground module. Here you have to calibrate you have to select the frame type first, which is the quadcopter, and we've already done it. So you select quad, and over here you select the X frame because that's what we are using right now. What high effect proper, you can use the plus as well. After this, we should calibrate the accelerometers and the gyroscopes. For doing that, we need to click on the calibrate button and place the vehicle level, then place the vehicle left, then click again, then place the vehicle right. It's very self-explanatory. You then place the vehicle nose down, that means towards the front, like in the video. Then you place the vehicle back. Nose up, then back, sorry. And after it's done, it will show calibration successful. You have to click it. And once it's done, you should disconnect and restart the controller to have the new tunes. Not tunes, new calibration. Then we should calibrate the compass. As you can see here, there are two compasses. There are two that are in use. One is unbound, it's just shown there. It's not actually present on the drone. You can remove it if necessary. We haven't removed it because it's not bothering us. Over here you have to select one primary compass and one secondary compass. The primary compass is usually on the GPS module, and because it has no interference from the motors, it's better to use that. And as you can see, my friend is gonna be calibrating it. I will click start here, and once I click start, he's gonna be rotating the drone in different axes, and the green bar here increases as the one magnetometer 2 calibrates itself. You can see different axes. You can spin it any way you want technically. Just keep spinning, that's all. And once it's done, you will hear a sound on the Pixhawk, and you'll see here calibration complete. One of the magnetometers has been calibrated, it shows success, and the second one is calibrated as well. It's important to remember that you keep the drone back, and to save the new calibration, you have to disconnect it and restart it just like we did in the axle calibration. Okay, after this we will calibrate the radios. The radio technically. There are 8 channels, and by using 8 channels we can control the drone. Yeah, we are using a Futaba radio, and I'll show you how to go on with it. Here you can see the channel monitor. The third channel is the throttle, and you can see the throttle increases. Then, yeah, sorry, just a second. After you calibrate, you'll see lines forming to mark the upper and the lower limits of the throttle, and you do it in all these switches and all the sticks that are available here. Do remember to click the calibrate button in the radio section. Do it for the switches. You can see this is channel 6. Keep turning all the dials so that it goes ahead and does it, And after everything is done, all the channels are correctly marked, you can click done. It will save the new limits inside the flight controller. Once this is done, we need to teach the ESCs the limits of the throttle. This is called throttle calibration. To do that, you have to put the flight controller in throttle calibration mode. To do that, you put the throttle up high and then connect the flight controller. Once it boots up, you disconnect it and reconnect it, keeping the throttle in the maximum position in the radio. After it's done, you can put the throttle back down. The flight controller is booted, and if you increase the throttle up, you'll see that the motors start spinning. And once you have done this, you can check if everything is spinning correctly again, and this should do throttle calibration for the ESCs. This is done because the Pixar passes through the throttle channel directly to the motors after this. Here you can see the servo output. If you're connected, you can increase the volume, increase the servo output accordingly as you need. Now we need to set the flight modes. I usually put channel 5 or this specific switch, as you can see here, and to put it in this thing to change the modes. The major modes I use are stabilize, altitude hold, and loiter. These 3 modes help us to control the drone better, and according to however the requirements are, we can change the modes accordingly using the switch. We save the modes, and then we should set a fail-safe. Over here we'll set the fail-safe to emergency return to land or return to home if something happens. Then there's a battery monitor. You can enable it. If you have a battery monitor, we have a power distribution board, and thus we have a battery monitor. When we'll select accordingly, we'll put the battery capacity as 5200 mAh, and we'll put the monitor as analog voltage only. If you have a better battery voltage monitor, you can use that. And you can see it's reading the voltage. You can restart it once again for everything to be saved correctly, and you can measure the voltage here using a battery tester and check the values that are read here with the value that is read on the flight controller or the mission planner itself, and make adjustments accordingly. It's pretty self-explanatory once you open the software after this. You can set a geofence, making a limit to where you can go, and now we can do some basic tuning. In the basic tuning, we're not going to change anything. The important part is we're going to do the PID tuning in the extended tuning section. I won't be going very deep into this section at the moment because there are a lot of explanations out there on the internet which will do much which will give a much better explanation on how to do it manually. There is an auto-tune function, and I'll tell you how to set it up. But before that, we need to make two channels. One assigned to one of the switches, like that one, so that we can assign it to the motor kill switch. We have to read it. It's the SWF, switch F. So we go into the radio controller settings, and in the 7th channel, that is what I prefer, we have to change it to motor emergency stop. This is one of the very important things. Yeah, as you can see here, SF. And you change it, the second one, to, let's say, this switch here. You read the switch name over there and put it in according to your radio. So channel 6 will be auto tune and channel 7 will be set to motor kill switch. And we can set channel 8 here to tuning something else or any other switch as you require. So as we set motor RC7 output to motor emergency stop, as you can see in extended tuning, here we can find arming checks, whatever you require and what you don't require. Over here, if any check fails or if you untick any check, it's on you, and the flight controller won't check before arming the drone or powering up the motors. This is the full parameter list, which we can go into later. Just a second, let me turn on the drone first. As you can see, when I try to arm, it arms. What the blue light says, it's armed. A solid blue light, and it says in the mission planner as well. And the motor starts spinning. Can increase the throttle to increase. I don't have any audio on this because there was no mic there. I'm dubbing it later. You can see if I turn on the motor kill switch, the motor stops. Yeah, and then when I turn it back on, it turns on again. We disarm it, and we've disarmed it actually, and let's see what do we need to do after this. Just a second, let me look. Yes. Yeah, now let's just fly it and see how it goes. After this, it's already winter here. This was recorded a little while ago. This is not me flying it. Yeah, so while my friend is enjoying the drone we just built, let me tell you a bit more about the flight modes. As I said, we are using 3 flight modes. You can read more about it on the Autopilot website, but let me tell you the gist of it. Stabilized flight mode is a very simple flight mode where it uses the EMU sensors inside to stabilize itself, and you have to control the throttle on your own. It'll self-level. It's more similar to self-leveling. Then there is altitude hold, where the drone will use a barometer to maintain its altitude. It'll try its best to maintain its altitude, and it'll also be using the self-level from the stabilized mode. So you don't need to control the throttle as aggressively as in the stabilized mode. The third mode is the loiter mode, where you can use GPS to do very good position hold, basically. This is another drone. We didn't tune everything in the first one. We didn't have enough time. That's why we're going to be showing you how to give GPS waypoints to the drone, and the drone will fly accordingly. Just before that, let me show you how the drone flies. He's taking the drone off, and I'll show you this drone as well, just a sec. This is a different drone using the 450 F450. I'm using a different frame or a different drone here because, as I told you, calibrating drones is a very important part of it. And we just calibrated the drone, but there was some problem. We couldn't calibrate it fully because of the snow. This drone was calibrated in summer and it flies really well. That's why we're showing up this drone. Frame is actually a very well-tuned frame. We use it to RC channel 6. And once you do it, you have to take the drone off, put it into altitude hold, put it at approximately 2-3 meters height and fairly away from you, and you should do this in a non-windy day. And once you select auto tune, you will see that the auto tune process will start and the drone will start twitching. And once the auto tune process is finished, the drone will stop twitching and you need to land the drone. And you'll see that the auto tune will be saved if you land the drone using the same tune and then disarm it, then flick the auto tune switch to off mode. And you need to do it for all 3 axes, the roll axis, the pitch axis and the yaw axis. Once it's done, your drone would be fairly tuned and you can move on to do other sorts of things. Here I'll be showing you how to add waypoints to make the drone move autonomously. As you can see here, we put 4 waypoints in the planning section of the mission planner. You can click on anywhere in the map, it will add waypoints, as you can see. You can zoom in, zoom out, check wherever you want to put waypoints. Hopefully not very far. You can write those waypoints to the flight controller by clicking the write waypoints button or save waypoints button, depending on your mission planner version. Once it's saved, oh, it was not saved yet, just a second. You click again, you make 5 waypoints, I guess, and then push the waypoints to the flight controller. I hope it got saved this time. And once you do that, once it shows up in your main menu, you can just click ARM and put it into auto mode or guided mode. Please remember that the first task should be usually take off or usually take off, and the last task should be land or return to land or something, because if not, there will be a check inside the flight controller which will stop flying. As you can see now, the drone started flying according to the waypoints. It will go according to there. We're recording from a Mavic. You can see it will make a square and then go to the 5th point, and well, fairly a square 5th point, and then come back to the launch part. After this, after it finishes the waypoint, if you haven't given any actions, it will just hover where the last waypoint was. You have to then give it an action, return to land, or whatever actions. He here was controlling the drone, that's why it went there, and now it'll go back. Hey guys, welcome back to the class. Yeah, so that being said, of course, not all tests are successful, and I can show you some videos where we failed flying the drone. Like, it fell, basically. Just a second. I mean, it is like we require it because we know that not all tests will always be successful, but we can give you a way that most of the time it will be successful. And of course, once you're experienced enough, all your tests will be successful. Just a second. I'll share my screen again. Here you go. Like you can see, the drone is flying pretty well for the timing, but at the end, I'll just show you that not all of our tests are always successful. Of course, we make mistakes, and that's why it's really important that you be careful when you're flying drones, because, well, you get hit by a propeller and it might not be very good. So we're trying to land the drone here, but we forgot that our battery was too low, and that's why, yep, there you go. You can see that not all tests are successful. We did manage to make a successful test that day. We recharged the battery, went back, tests were successful after this. Look. Yep, flying stably as we wanted to. So it is very important to remember when you are flying a drone, like, of course, to be careful and, yeah, take all the necessary precautions. Up until now, if you have any questions, please let me know.
Maybe it didn't understand. 3 minutes already, so yeah.
Yep, as you can see, it lands fairly nicely. Yep, that makes it a successful test. So yeah, let me know if you have any questions up until now, and if not, we can move on to the short programming part. Yeah. Okay, before I continue, I want to talk to you about the Raspberry Pi connection to the PixHawk, a simple connection, I guess, yeah. So if you want to connect the Raspberry Pi with the PixHawk flight controller, you only basically need two pins, that is TX-RX. Let me just draw it out to you. Making the slide. Just a second, let me just make this like a whiteboard. Yep. I hope you can see my screen. Yep, here. Let me just draw it out to you. Yeah, so you have the PixHawk. And you have to connect it to the Raspberry Pi. Just a second. Raspberry Pi or Jetson or anything. Basically, what you need to do is, well, just a second. Let my screen load up very properly. Yeah. Yeah. So in the Raspberry Pi, you have something called GPIO. Or general purpose input output pins. And you need to connect one of those pins, depending on your program, you need to connect these pins to the telemetry 1 or telemetry 2. Telemetry 1 or telemetry 2 in the PixHawk. The pins that you need to be aware of is basically only these pins. That is TX, which goes to RX over here. And there is TX, then there's RX, which goes to TX over here. Basically, in reverse, the TX pins to the RX pins, so that the transmitter goes to the receiver and the receiver goes to the transmitter. Okay, and then you need to be wary about another pin, that is the 5 volt. 5 volt, and of course, well, you can connect any ground from the PixHawk with the Raspberry Pi. These are the 4 connections that you would be needing for connecting the Raspberry Pi with the drone. Of course, it depends on your program on what you want. You can, of course, go into another thing that is directly connecting the Raspberry Pi using the USB of the PixHawk. So that's why you use the PixHawk. One of the major reasons is the PixHawk has a micro USB port. The latest ones have Type-C, of course. Type-C, but wait. it has a micro USB port, usually on the right, somewhere over here. You can just connect it directly using RPI or any OBC. You can connect it directly using USB to this. And of course, you need to change the program to go for a UTP a USB connection instead of the TTY connection it looks when it's connected to the serial port of the Raspberry Pi using the TX and RX. Yep. So that being said, I can move on to talking about software in a loop. And let me just show you before I go ahead. I can just probably show you a bit of the drone I have made over here. Just a second. Yep. I don't know if you can see my screen or not. See me, actually, yeah. So, yep. Over here, I have a small drone. If you have any questions about this, I can show to you. If you can see over here, this is the camera. Okay, there's the flight controller. This is a small F4 flight controller inside over here. Okay, and then there are, of course, motors and propellers. This is a small drone, of course. That's why this is the video transmitter over here, because someone is here. This is the video transmitter here, and this is where you connect the battery to it. And then, of course, this doesn't have an onboard computer, but it has a small chipboard that is right around here, which lets me connect via Wi-Fi and control it autonomously if required. This is a controller. This is one of the cheap controllers that you can buy if you want to test drones for yourself, build drones and test drones. This is one of the first controllers that you should buy because, well, it's cheap and you can source it from anywhere. It's the beta FPV controller. Anyway, moving on. If you have any questions, once more, let me remind you, the drone has 3 axes and I can show it to you better right now. So let's say the drone is facing forward. This is forward. This is the pitch axis when the drone moves forward, like this. This is the roll, pitch, and then there is yaw. Okay, yeah. So use that when you're programming drones, or use that when you're building drones properly. Yeah, just for a demonstration. Anyway, I'll share my screen again and go ahead into. Okay, so I know that not all of you have drones already built, and of course you need to test drones. So that's why you need to go ahead and run a simulator. You can have multiple versions of a simulator or multiple simulators if you want, but we are going to be using SITL in Autopilot. You can use PX4, you can use Betaflight Simulator, you can use the DJI Simulator, whatever you want, you can use it. But we are going to be working on the Autopilot Simulator, and the task demands you to use the Autopilot Simulator. The Q ground control ground station can connect to the other simulators, but I don't know how much deep you have worked with the drones or not. So that's why I'm not going to be going into that. The software in loop, all the instructions that are given are for the Autopilot Simulator. Yeah. So SITL, or software in a loop, allows you to run Autopilot on your PC directly without any special hardware. It takes advantage of the fact that Autopilot is a portable autopilot software that can run on very wide variety of platforms. Your PC is just a platform that you can run on. Okay. When running in SITL, like the software in a loop, the sensor data comes from the flight dynamics model in the flight simulator. The Autopilot has a wide range of vehicles or simulators built in, and it can interface with several other simulators as well. Of course, software in a loop can be used with MATLAB, it can be used with Python. I'm going to be showing you with Python, but anyway, you can use other various different things. You can use SITL by using the following command after you install it. That is simvehicle.py, rdcopter, console map, like whatever this thing. And yeah, of course, if you want to know about it in detail, you can read it directly on the Autopilot website. Here's the link to it over here. You can go ahead. Okay, let me just show you this thing while you're working at it. So for the winter school in this time, we are going to be asking you to install, well, these are the recommended things, but these are all you need. Like if you have a virtual machine, install Ubuntu in it, or you can install it directly on a computer and install ROS in it. If you want to go for in-depth programming, which this is optional, but like it's suggested to have. Then there is Mavros, which is also optional unless you want to use Python scripts to run your drone. Then you should clone the Autopilot repository and build it and use the, just a second. Yeah. Yeah, and build it. You should use the Copter version and the Cube Black because that is usually the most stable version here. And of course, there are references. And yeah, if you want, you can go ahead and go ahead with this thing. Let me go ahead and show you my version, like not my version, like my implementation. Here is my virtual machine. I hope you can see the screen. Yep, I have already installed everything, so I'm not going to be showing you the install part. That's your homework, and I've already written the script. So I'll just launch it and show it to you. And this is what you should expect after you install it. Yep, as you can see here, this is the drone here in the simulation environment. I can show it to you from a bigger distance over here. And now, yeah, what if you have installed everything correctly according to, let me just show it to you again. According to the instruction guide given here, you should be able to run this command to run the simulator to get something of a similar output, just like this. You'll have an environment where you can see the drone, and well, of course, this is called Gazebo. I'm not going to be going in depth. Yeah, and you can have various controls. This is a small ground station over here where it will give you all the information of the gyroscope, or how, if the Autopilot is ready or not, if what kind of external Kalman filters it is using, and if the alignment is complete, and the battery percentage and whatnot. Okay, so what I want you to do is, in the given task, when you will do the task, I'll show you what expected output you should have, but I'll just go ahead and run a small program. I can just show it to you, program over here. If I go ahead and go to Autopilot, just a second. Here. Okay, so this is a small program I've already written. I'm not gonna describe it, but yeah. So to control the drone autonomously, you should usually use the loiter mode. Let me just remind you, I don't want this exact thing from when you guys are doing it. You don't need to program anything if you want. I'm not sure how advanced you are in programming, so I'm not going to give you a task related to programming. So I'm going to give you an alternative, but just for this thing, I'm just going to show you what you can do when you are using this kind of a system, like a programming system. Okay, so you need to connect. Since this is a internal connection, a software in loop, you need to connect to the computer itself. That's why you're using UDP, or we're setting up a Mavlink connection. It'll wait for a heartbeat over here. Wait, we have someone coming. Okay. By the way, everyone, if you can rename yourself to the names that you gave while you were signing up, that would be great, because then we can mark you on your assignments accordingly and mark your attendance accordingly. Please do that, and it would be really helpful for us if you do it. Anyway, moving on. We're going to be using the loiter mode. I can show you what the modes are once again. Just 1 minute. Yeah. So if you can see here, we have a plethora of modes. There's acro, there's air mode, there's altitude hold, auto tune, brake. Like you can just read about a lot of modes on the Autopilot's website that is over here, and different modes of different functions, but we are going to be using the loiter mode. It holds the altitude and position and uses GPS for movements. The thing is, it uses GPS for getting the word frame, that it translates it into the body frame so the drone moves accordingly. Okay, and of course you need this mode or auto mode. But here we are using loiter because we're going to be changing the movement of the drone as and when required. Okay, go ahead. Yeah, we have a question. Is there a specific requirement of the PC? I'm sorry, not really. Jimax, thank you for your help, but not really. For the task that I'm going to give you, you need Linux. So it will be preferable if you use Ubuntu. It's over here. It's given all the information is given over here. Ubuntu 18.04. You can use a later version. And you should have at least 8 GB of RAM for working on this. That is one requirement because, yeah, it's pretty heavy. The Autopilot software, when you're running it inside the computer, software in the loop, it's pretty heavy. I have a more powerful computer, and that's why I'm using a virtual machine to show it to you. For a virtual machine, for just the virtual machine, you need at least about 8 to 10 GB of RAM and 4 processor cores. I'll just write it down over here. Yeah, you can just, again, I'm just going to copy my GitHub link. You can see it over here. That's it. Okay, up until now, if you have any questions, let me know. And yeah, moving back to the program over here. Yeah, this is a Linux machine. Just so that you're aware, this is a Linux machine. Yeah. Yeah, this is a full Linux machine. This is Ubuntu 18.4 LTS, and it has around 15 gigs of RAM. That's why I'm telling you, this is a heavy, this is a heavy software. You need systems to run it, a good system to run it. Okay, anyway, you can, after you select which mode you want, you can write auto mode or you can write guided mode, whatever mode you want, and get the mode ID of the mode that you're using. After you have done it, you can just set the mode ID here and then call the entire system using the initializer here. And then after that, you can arm. This is the command for arm. And then you can take off. And then you can change it into guided mode, do whatever you want, and come back. Let me just run this short script to show you what happens when I do. Just a second. What? Just a second. You see the drone starts up. I can show it to you again. It takes off, goes into guided mode, holds position, and eventually it will land. Yep, if you can see here. It usually waits for 15 seconds. I don't want it to wait for 15 seconds, so I can just go into this, or the ground station part of it, and just give mode. Well, just land. Yep, it's gonna land eventually. Yep, if you can see here, sorry, just a second, it lands here. You can even give commands like take off from here, like maybe like arm. For taking off, you need to, of course, arm the motors. So that ARM. Yeah, just give it the, sorry. Go for arm throttle. It'll arm the motors over here. And then you can say take off 5. So it'll take off and go at a specific position. Wait, the mouse isn't fast enough. Yeah, and hold the altitude at 5 meters. If you can see, I'm giving it commands and it's doing it. Yeah. Okay, we have some questions. Let me go ahead. What libraries do we have to use to be well versed in try to code similar to what we just saw right now? And also where we can learn to write the scripts to the drone. Yeah, sure, of course. Let me show them to you directly. It's called PyMavLink. You can read about it here. Let me just give you a link to it. This is a library that I'm using, and you can read about it. Of course, if you need, like, it's for beginners, it's a bit hard to get into. Yeah, Samuel Bugle, your laptop has 500 gigabyte hard disk. Is Robot Control. Yeah, of course, 500 gigabytes is more than enough. Yeah. Okay. Anyway, for Sujit, so Shutnayak. Sorry if I'm pronouncing your name in a bad way. My mistake, Shutnayak. Yeah, libraries. I'm using PyMavLink for this specific script, but if you can see, if you open my GitHub, I've used ROS, I've used OpenCV, I've used different, like, more like well-versed. So this thing here, you can see for detecting using image recognition to move the drone to a specific position. But since we don't have time, it's not like we don't have time. It's more like it might get a bit too advanced for one single class. And that's why I'm not going to be going into this. But there is the code online available if you want to use it. Okay. And yeah, I'm using PyMavLink for the libraries. This is the link to install it. And of course, you can use all sorts of modes and all sorts of, well, you can do a lot of stuff using PyMavLink. And you can read about it in this GitHub. Of course, again, I don't expect you to use PyMavLink for the assignment I'm giving you. I'm going to be showing you a simpler method on how to do all this stuff using a ground station. But anyway, I can just go ahead and land. It'll land automatically. Yep. Let me try and see any other codes that I have to show you. Okay, let me try to show you what you can do with these. So I have written a program so you can go to a specific GPS point that is here. You're giving a latitude and longitude. It should go to this point. I have no idea where this point is in the map, but yeah, let me just show it to you what happens if I run it. Just a second. Yep, it's connecting to the vehicle and it's running basic preamp checks. And then, of course, it goes out into the open. Yep. And then it's going to the GPS point. You can see, moving towards the first waypoint. I'll show you a better view of it, probably over here. Yep. Going to the first waypoint. I have no idea where that waypoint is, but yeah. Probably a bit too far. Shouldn't be, yeah. Oh, it reached towards the first waypoint. And yep, here you go. And then it'll start landing over here because that's the command that's been given. Yep, slows down a bit. That lands. You can, of course, run advanced scripts on it. And I'm going to be showing you an example or an output of the advanced script because, well, yeah, because it might be difficult for you to get into right now, but I'm just showing you what you can do with it. Just going back to my presentation. Just a second. Okay. Paulo Zik, you're a beginner to this, no problem. That's why after this, I'm going to be showing you an easier version without programming, how you can control the drone without programming using a ground station. But just for now, I'm just showing you what you can do if you like put the extra effort and learn programming and to do it. Look here. If I show you, if I use an autonomous landing, I just made this package, and you can use, like, the code is available here on my GitHub, like on the link I shared. If you can do it, it'll take off and land on the red square. You'll see if it'll take off now. Sees the red square in its camera, goes to the red square, and eventually will land. Just show it here. It aligns itself on the square so that it lands exactly in the middle. Well, somewhere in the middle where it sees the square or the landing pad, and it'll land. Well, our lab does have a research paper on this. If you want to read more, we can link that to you after it's published very well. Anyway, moving on. We have exhausted most of the time for our class, and that's why I'm going to be going into showing you the easier method of controlling the drone using a ground station. Let me give you an example. I'll just close everything so it's just easier for you, and I'm going to be launching it again, so you're going to be seeing what I'm seeing after you install the program properly, like as you were supposed to, if you install the program, if you're as given in the GitHub link. And remember here, I'm using a launch script. I haven't given the launch script because since you're learning, you need to write each and every command as you were supposed to. You can see again what you have to do on the GitHub link. That's your task. I'm running it again just for showing it to you. Here you go. And if you can see here, there's gazebo, and I'll just show you how to control the drone using the application called Ground Control. So when you download this application on your Linux machine, it automatically detects it as an application that stores it. You just have to double click it and wait for it to launch.
Stabilize flight mode.
If you can see here, it's already loaded. And the Ground Control ground station has started. And you can, of course, do all the same things. Yeah, of course, Surajit, it can be run on Windows. Ground Control and Mission Planner both can be run on Windows. But it's easier, but since you're using, well, it can be. That's the short answer, but it can be difficult to get the software running, the settle software running on Windows. It's not fully developed properly yet. It's not fully developed yet. Anyway, you can look it up on the Autopilot website. If you want to run on Windows, definitely you can go ahead and run it on Windows. But the instructions might be a bit different depending on what you're doing. Anyway, I can show it to you that if you want to take off, just take off over here and it'll just take off.
Guided flight mode.
It goes into whatever flight mode you want. And if you can see here, it takes off and holds the altitude at 10 meters per second. And you can see all the information over here. And as the drone flies as well. The altitude is at 10 meters, the ground speed is 0.1, the flight time is 16. You can do whatever you want. Okay. I will just say land because I want it to land right now so that I can
land flight mode.
I can show you what different modes you can use. You can see, let's wait for the drone to land. Yep, and the drone landed. Now,
Disarmed.
let me show you how you can set a mission, just like I showed you. Let me remove these waypoints if I can. Yep. Just saying. Yep. Yeah. And let me show you how you can plan your own mission. Now I'm going to be making a square, like make the drone fly in a square. Okay. Here, 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 and then we're done. Okay. So I'm going to be making the drone fly in a square, and I'm going to be changing the speed as well. I can adjust what altitude I want. Let's say I want to go to 5 meters. Then apply new altitude. Yes, I'm going to be applying this altitude to all this thing, 5 meters. And let's say I want to go at 5 meters per second to the first point. Then I want to change it to, let's say, flight speed to 7 meters per second or 10 meters per second. I'll go for a different this thing. And then after that, I want to go back to 5 meters per second. Just a second, I can do that as well over here. So the mission start, it takes off and goes to an altitude of 5 meters and then goes to the first waypoint and turns right, goes to the next waypoint over here, and then goes to the last waypoint over here and comes back and lands to the position where it was. Okay, let me just, this is planned. I can upload the mission to the flight controller, and I can go back and then I can just start the mission. If I start the mission,
Guided flight mode. Armed. Auto. Missing takeoff command. Flight mode change failed auto.
If you can see here.
Disarmed.
I forgot to give the takeoff command. Let me just go ahead and give it the takeoff command over here. Yep, I gave the takeoff command. I just missed it. Remember, you always need to give a takeoff command, because if you don't take off, how will you fly to the nearest point? Let's go back. And of course, over here, you can see what mistake you made. Like I said, I didn't give a takeoff command. Here you can see. Now I'm going to start the mission again and go to gazebo.
Auto flight mode.
Look.
Potential thrust loss 4.
You can see it's going to go to the given position. I'm going to be, it's really hard to track on gazebo. So you can see over here in the mission planner control, the Q current control ground station where your drone is going. It is moving to the first waypoint at a speed of 5 meters per second, well, as much as it can reach. Slowly move to the position given here. It's pretty far, so you can't see it over here. That's why you can just rely on this screen. It goes to the first waypoint. Then after that, it will make a turn and go to the next waypoint. You can see the second waypoint is highlighted. And it starts moving to the second waypoint. I set a speed of, I set a speed of 5 meters per second. Yeah, as far as I remember, for the second waypoint. And remember, of course, it might not be able to reach a full speed of 10 meters per second because I'm using a laptop and a virtual machine. But if you install the whole software natively and give your whole computing power to the simulator, of course, it will be able to simulate it much better and reach higher speeds. Anyway, if you can see, it's going to the second waypoint. And you can see all the telemetry data on your right in the ground station. If you want, you can also view this, or not this part, this thing. After it reaches the second waypoint, because it is going to make a right turn and go to the third waypoint. Yep, as you can see, it goes to the third waypoint. It's going to increase its speed. If you can see there, it's going much faster. It's taking like 6 or 7 meters per second. Well, according to the drone, it's 10 meters per second, but the ground speed is 6 or 7 meters per second. It's going to the third waypoint.
Low battery, 29% remaining.
Then after it reaches the third waypoint, it's going to go back to start. Let me just zoom in so it's just better. So when the drone comes back, we can see it come back to the start position.
Low battery, 22% remaining.
After that, it'll just start going back to the home position, which you can see there. And it uses the same 5 meters per second speed to go back to return to home. That's because that's the general speed set. Of course, remember,
Low
like,
battery, 14% remaining.
Yeah, the final waypoint is not a waypoint, it's a return to home command. So it is going to use whatever orientation it has instead of turning the drone towards the waypoint and moving.
Low battery, 11% remaining.
So don't worry about the low battery warnings because this is just a simulator again. The drone is not actually going to fly out in the sky. Well, it may, but not in this instance. Well, I hope not.
Low battery, 7% remaining.
Let's wait for the drone to come into view.
Low battery, 3% remaining.
It's near. Look, the drone is here. It's coming back to the position it started.
Low battery, 0% remaining.
And then it's going to land. You can see over here. And it eventually decreases its altitude over here, and then it can finally land. Your task is to use the Q ground control software to plan your own mission. Whatever you plan, like, it shouldn't be a square because I just showed it to you. You should take screenshot, you can take a video, you can take whatever you want. I need you to plan a mission using Q ground control and the Citl software, and then finally do whatever. Maybe write your name in the sky, maybe make a circle, maybe make a rectangle, or do whatever. I want you to plan a mission using this Q ground control software and send me the screenshots using the given link. I'm going to close everything. Like, I hope you got this. If you have any questions, please let me know, because you need to do this.
Communication lost.
Just a second. I'm going to be disconnecting everything so that I free up some system resources so I can show you where you can upload everything. Oh, wait, go ahead. There's a question. I have my VirtualBox, I have my VM box in my machine. I just downloaded it a few days back, even didn't throw in my video script to configure everything so far. Well, the material is in this. Like, this is all. This is it. Like, you want me to help you set up the VirtualBox or what? Yeah, the installation, everything is given over here. like in the link, all the instructions on how to install the software. You should have Windows, Ubuntu, and you go to this link over here, Mavros installation, and all the instruction is there. Then you can go to the Autopilot repository and you run these codes. You don't even have to go there. You just git clone this, cd Autopilot, run each command one by one, and you will be able to install everything. All the commands are given here. No, the ROS, well, the ROS is given over here. This is the instructions. But I didn't show you anything with ROS. You don't need ROS to run the example that I showed you. It is a very good thing to have, but you don't need it to run it. But it's a good to have, of course. This is the link. All the instructions here are very well written. You can just set up your sources, set up your keys, installation, and then this is the command. That's it. Nothing else. You don't need to do anything more. And then, of course, you need to set up the environment. This is all optional, but yeah. Just run this, install the full Merrick desktop, okay, and then run the Autopilot repository. And then after that, if you want to use Gazebo, use Gazebo. If not, I'll be showing you an alternative to that as well, because not all computers will be able to run it. As you said, Surajit, that you have VMbox or VMware, not VMware, I'm sorry. Most likely you're using Sun VirtualBox. That's what I hope. You might not be able to run Gazebo in that, so I have an alternative for you. I can show it to you after just right now, just a second. I'll show that to you. And then if you run this specific command, everything should be on your screen, just as I showed you. You can then start the Q ground control software and then plan the mission as I showed you, okay? Once again, for the alternative I was talking about without Gazebo, let me just go ahead and not run Gazebo. Instead, I'm going to be using this. So the simpler version. And yeah, for you, if you're using it, take note of this specific command. You don't need to run any other commands. Just run simvehicle.py with these specific parameters over here. I'm highlighting it on my screen. Okay. And then you need to launch it. Of course, you're not going to be using this launch script because that's mine. You have to type the whole command. You can see there is a small map over here with all the information wherever you need. Yep, so you can see the drone is here and this is the map, okay? And once you have this screen, you can give it commands. So for example, I can just ask for it to, let's say, go here, fly to. Let's say the altitude is 10 meters. 10 meters, it'll take off. Look over here. Just a second. It goes to guider, it takes off into that altitude. You can see over here. Oh, there's a, yeah. So that's here. Say 10 meters per second. Yep, over here, you can see we need to wait for GPS, just a second. Back to guided mode. Yep, once you put it to guided mode, the mission is accepted, it will take off and then eventually go to this point. It takes some time. You need to put, it's going to be arm motors, and then it will take off and then eventually go. Yep, if you can see my screen, it's moving to the new waypoint as given. Yep. So if you can see my screen, the drone has already moved to the new given position over here. Excuse me. And you can use this as a simple ground station for your project. Of course, ground control is a simpler option. Everything is given here. It's much better. Let me just show it. Go ahead and show it to you.
Communication lost. Stabilized flight mode. Communication regained.
It's gonna, okay, do we have a chat here? Yeah, no more. Okay. If anyone has any questions, do let me know. Of course, we're gonna be solving them one by one. Yeah. Once again.
Sorry, but when is the deadline to submit the tasks?
Well, I'm not sure about the deadline. Misha, can you help me out? When is the deadline?
Okay.
Yeah, like let me just get that confirmed. Misha?
Yeah.
Yes. When is the deadline to submit the tasks?
I guess the deadline is the end of our winter school. So
okay.
Yeah, you have at least you can, yeah. Firstly, you can ask questions to Mainak if you have, of course. And I wanted to tell you that tomorrow you will have a time to make this actual assignment, to finish it. And as we told you earlier, guys, in our site, we have a button where you can upload your assignment. And if it's necessary, I can show you a bit later how to find the specific form to upload your homework.
Yeah, thanks for mentioning that. I'll just show it to you right now. Look, if you open the fitac.ru robotics website, the website you signed up from, you can see here, upload your reports. You click on your upload your reports. And over here, this is the form which you can use. So you can give your email, your citizenship, fill up this form, and select advanced practical task 1, that is advanced intelligent drones. That is the masterclass you just attended. And over here, if you have any explanation, if you want, and if you want any files, you can upload it in doc or PDF format. And if you want to upload a video, you can just record your screen and upload it in YouTube, or give me a Google Drive link and I will review that here. Yep. And then finally press submit. If you have any questions, send me an email. You can send Misha an email.
Thank you so much.
Go ahead for it. Yeah, that is all. And that's it. If you have any questions, let me know. Our time is, we have maybe 5 minutes and we can discuss if you have any questions, and we can go ahead and finish this thing. Once again, this is the link. And if you want to contact me, well, yeah. Of course, if you want to contact me, here is my contact information once again. Yeah. Thank you, Tekle, for attending.
Thank you, Mainak. Thanks a lot for
Thanks a lot, Misha.
For your masterclass.
Thanks,
guys, a couple, I want to tell you just a bit information about our work in this here in winter school. So let me remind you that tomorrow we won't have any online classes. You just have a time to finish your assignment, which Mainak already give it to you. And tomorrow, I mean 16th of February, and on Thursday, 17th of February, just before the next masterclass, you will have 30 minutes with Mainak to ask some questions, ask any question that you have. Maybe Mainak will tell you some extra information, or just leave a feedback that you want. And after that 30 minutes, on 17th of February, we're gonna start the second masterclass. It will be, about the computer vision and neural networks. Please write something in the chat who wants, is everything clear? And if there is no questions, so I guess we can finish today this meeting. And yes,
Ali Zishan asked, there's a second class. Yeah, so the second class will be on, as far as I know, we can go ahead and see what the second class is. You can view it over here. /robotics. Just a second. Yeah, you can get all the information. Yeah, if you want the clear information, go ahead. The task is given here in my GitHub page. This is the task. Use the Q ground control ground station to connect to the simulator and upload 4 waypoints, the flight navigation system, and launch the mission. Record a video or take multiple screenshots and upload it to the given portal, if you can see here. Yeah, if you submit, if you finish today, you can submit the project today. Yeah, of course, no problem. Yeah, and let me, for Ali Zishan's question, let me just show it to you. The second class will be at this specific time. Misha, this is it, right? This one, Masterclass 2 Computer Vision.
Yes, you're right.
Yeah. Mm-hmm. So
whole,
that is on February 17th. Yeah,
go ahead, information Misha. You have the whole information you can find in our site. Please, I guess everyone knows the address of this site, but let me just in case send it to you again. In the chat, you can find the whole information about our winter school. You can find there. Also, the timetable is there. The next class will be, as Mainak told you, on Thursday, computer vision and neural networks. Just before it, it's 17:30, 5:30 p.m. in Tomsk time. You will have just a bit, you'll have time with Mainak to discuss today's masterclass. And after this, we're gonna continue our winter school.
Yeah, so I have a question again from Saurav Das. Yeah, we have to follow the steps as discussed in the GitHub link. Yes, you have to follow the steps. And if you follow the steps exactly given in the GitHub link, or you can just look it up. You can see my other projects over here. github.com/ if you use this link, yeah. So, and the link for the assigned session is here. If you follow all the instructions given in the GitHub link, everything should be just as I showed you. You just need to open Q ground control that you have to download on your own. Remember this Q ground control. If you have to download this on your own. Once you download this on your own and run it, well, let me just show it to you just to be safe. Control. This is the software you need, and if you download this, it's already given here. Q ground control ground translation. Okay, and if you download this on your Linux machine or Windows machine, this already has for Windows or these things. It'll automatically connect to the ground control, the simulator that you're using, and then give you the interface that I showed you. This specific, this interface. Okay, it won't have the waypoints because I made them, but yeah. Let's see. Clear it. It should look something like this. Yeah, your information should, your ground station should look something like this when you start. Yeah, it should look something like this. And then I showed you what to do to get to what you need to do. You need to upload at least a minimum of four waypoints. You can have more, of course, but yeah. Recording a video would be great, but if not, you can just take multiple screenshots. and then upload it in a PDF or a Word document in the form over there. Yeah. If there's anything else, we could go ahead. Once again, here